Welcome to day 10 of calculus. Today we're going to talk about average rate of change. If you remember one thing from today's video, please remember that it's quite frequently the case that finding the average rate of change is as simple as finding the slope between 2 points. So you've seen this before. You've seen this in questions like a car drives 70 miles per hour in 2 hours. What is its average rate? You've done things like this for a long time. So if you go 70 miles in 2 hours and you want to know what the average rate of change is, you're going to divide 70 miles, the distance, by the time it took. So the average rate of change is 35 miles per hour. Keep in mind, this does not mean that the car necessarily drove 35 miles an hour the whole time. It just means that the average speed in this case was 35 miles per hour. So let's talk about finding the average rates of change of defined functions like this one. So we're talking about f of x is equal to 3x minus 4. We want the average rate of change from x equals 5 to x equals 20. In order to do this question, you first want to find what are the actual points when x equals 5 and x equals 20. Remember, I said that finding the average rate of change is going to come down to finding the slopes between 2 points. So if you plug 5 into this function right here, 5 times 3 is 15. 15 minus 4 is 11. You have the first point, 5, 11. And you have the second point, which is going to be 20, comma. We'll plug 20 into here. You get 3 times 20 minus 4. What point is that? That point is 20, comma. Is that 60 minus 4? 56. So we have 2 points. We have the point when x equals 5 and the point when x equals 56. And you'll probably remember that finding the slope is finding delta y over delta x, which is y2 minus y1 over x2 minus x1. So in this case, it's going to come down to, for these 2 points right here, you have 56 minus 11 over 20 minus 5. So in this case, it's going to be 45 over 15, which is 3. So the average rate of change of this function from 5 to 20 is 3. Now what happens if we check it from -4 to 6? The first thing we do is we find the 2 points when x equals -4 and x equals 6. In that case, it's going to be -4, -16, and 6, 14. We set up the y2 minus y1 over x2 minus x1. Oh, and look, this time it came out to be 3 as well. It is totally possible to have the same average rate of change in 2 sections in a function. Absolutely. So let's do a couple more. In this function, we have x squared plus 4. So remember, we find our 2 points. Starts with x equals 0 and x equals 2. So it'd be 0, 4, and the point 2, comma 8. And you find the slope, which is going to be 8 minus 4 over 2 minus 0, which is 4 over 2, which is 2. Exciting, yay. Doing the same thing for this example right here with this function. Plug in 2, we know it's going to be 2, comma 8. We plug in 4, it's going to be 4, comma 20. And when you do this one, you end up with, which is 6. And let's see why that's visually true. What does the function x squared plus 4 look like? Well, it's a parabola with a y-intercept of 4. So it goes up like this. And what are we doing here? I told you finding average rates of change is finding the slope between 2 points. Well, if I go from x equals 0 to x equals 2, that's right about here, make it green, here to here. I'll make that curve a little better here. Let's clean that curve up a little bit. So we go from 0 to right here, and we make this secant line. So we found the slope there was 2, so that's from 0 to 2. But if you go from 2 to 4 here, here's 2 to, let's say that's 4. I'm exaggerating here. See that? We just measured the slope of that line. So we said that the slope here was 2 and the slope here was 6. And that kind of makes sense because as we move to the right, this curve is getting steeper. These lines that I just drew in, connecting 2 points, not the 6, but the 2, this line right here, the line between here and here, is called a secant line. Connecting any 2 points on a function is going to be called a secant line. So for example, let's say I had a function traveling along like this, and I connected this point to this point. This would be called a secant line. So if we're dealing with the same function and we wanted to do the same thing but from 4 to 6, we'd expect it to be greater than 6 because as we move to the right on a parabola right here, the secant line should be getting steeper. So if we find the points and write out the difference quotient, We found the slope to be 10. So now let's generalize here. Let's generalize here, meaning let's go from x equals 6, to 6 plus h, meaning h will be in our answer. So we've kind of been doing this before. We went from 0 to 2, we went from 2 to 4, we went from 4 to 6. We kind of had a difference of 2, but let's see what happens when we go from 6 to 6 plus h. Remember, h will be in the answer. The first thing we need to do is find the points. And remember, our function is x squared plus 4. That's our function. That's our g of x right there. So the first thing we need to do is find our points. What are our points? Well, you plug in 6 into this. We already know if you plug in 6 into there, you get 6 squared 36 plus 4 is 40. But what happens when you plug in 6 plus h? Well, g of 6 plus h is going to be 6 plus h squared. That's the x squared part right there. And then you have plus 4. So you could multiply it out, or you could leave it like it is for now, because we don't have to do it out yet. So what's the point? 6 plus h, comma, 6 plus h squared plus 4. So these are the 2 points we have. We have these 2 points. We're going to do the exact same thing. Our slope is going to be the y value right here minus this y value. So what's that going to be? It's going to be 6 plus h squared plus 4 minus 40 all over 6 plus h minus 6. Those are the 2 x values. So 6 plus h minus 6. So let's simplify this. That would be the slope. If I just asked you for the slope, that technically is the answer. But let's see if that simplifies a little bit. So I multiplied out the numerator. And now you'll notice that we have 36 and 4 is 40, but then minus 40. So those all cancel out. And what are you left with on top? H squared plus 12h over h. Factor out an h from the numerator. H plus 12 over h. What cancels? Cancels out, and you're left with h plus 12. That would be the final awesome simplified answer. That tells us the slope between the points, and these are the 2 points. Here's point 1 right here, and here's point 2. The slope between those 2 points is h plus 12. Should make a little bit of logical sense, because if we're looking at the right-hand side of this parabola, if this is where x equals 6, as we take the secant lines further and further away, those slopes are going to get bigger. Just like h plus 12. So there's this great point here. Slope of the secant line, if it's getting larger, if the ARC is getting larger, the average rate of change is getting larger, the function is concave up. So if I have a parabola that looks like this, and I have a secant line slope that's anchored here and getting larger, is that line getting steeper? It is. If these lines are getting steeper as these points move to the right, you call this concave up. And conversely, if the opposite happens, let's say we ended up with something like this, if we do the same thing and do these secant lines right here to there, these lines are getting less steep, so this would be concave down, concave. One important thing to note about both of these graphs is that they're both increasing. As x gets bigger, so does y. Y gets bigger. But one of them is concave up and one of them is concave down. So you can be increasing but be concave up or concave down. Similarly, you can be decreasing and be concave up or concave down. So let's look at this graph and find 4 different characteristics. First one asks, on what intervals is the graph below increasing? That strictly just means as x gets bigger, y gets bigger. This has nothing to do with concavity. These have nothing to do with concavity. So as x gets bigger, meaning as you move to the right, increasing means y gets bigger. So as x gets bigger, where does y get bigger? Well, it looks like it's getting bigger from here to here and also from here to here. So that's where it's increasing. As you move from left to right on the x-axis, where is the function increasing? What about decreasing? Well, it's going to be decreasing where it's going down as x goes from left to right. What about concave up? It's like think of it also as a bowl facing up. Where is it concave up? Well, it's going to be where the slopes of the secant lines are increasing. So concave up is where the bowl is facing up. And it's a little hard to see, but it's definitely concave up here and here and here and here. The bowl is still facing up, it's still facing up, it's still facing up, and then right about here it stops. It turns to concave down. So concave up is where the bowl is facing up and the slopes of the secant lines are getting bigger. Now what about concave down? That's where the bowl is facing down. So if you had an upside down bowl, and that would be starting here and going down. Now you might look at this and say, well, there are some interesting points here. Well, there really are. There's a great point that's right here, a highest point and a lowest point, and then something happens here, the concavity changes. We will learn more calculus to find those exact points, but the important thing now is to realize where the function is increasing, which is yellow, decreasing, which is blue, highlighting, and then where is it concave up? That's when the bowl shape is faced up, happy face. So concave up is happy, concave down is sad. So where do you see the smiley face? Well, you see it right here. And where do you see the frowny face? Well, you see that right there.